Okay, so welcome back to Astronomy Colloquium. And today we have a guest from the other side of the world, but north versus south as opposed to east versus west. So Rodrigo Herrera-Camus is a professor at the Universidad de Concepción in Chile. And I first got to know Rodrigo back when he was a Fulbright scholar at the University of Maryland. So he was working with my longtime collaborator, Alberto Bellato, and we've had exchanges and collaborations on various things. And I've really been impressed at how Rodrigo has diversified his research portfolio over time. So after finishing his PhD at Maryland, he went to the Max Planck Institute for Extraterrestrial Physics in Garching, worked with Reinhard Genzel and his group. This was before the Nobel Prize, I guess. So
yeah, I always dreamt that he will get the Nobel Prize while I was there to see if I was going to be invited to the celebrations in Sweden, but actually. No, I mean, he got the prize 1 year after I left, and there was no celebration in Sweden.
Yeah, it's a pity. I'm sure he would have enjoyed a celebration. And then I guess, Rodrigo, you started your current position in 2019.
Yeah.
And he's still affiliated with Max Planck as a group leader, as a Max Planck partner group leader. And he's been working on a variety of topics. He's going to talk to us today about atomic and molecular outflows from galaxies. And yeah, I guess you can go ahead and start your screen sharing. Rodrigo.
Super. Well, thank you very much for inviting me today. I think it's just I mean, the only time I've been visiting your astronomy department was when I was a first-year grad student, so almost like 11 years ago. So it's just great to be back now virtually, of course, to talk about the science I've been doing now here in Chile, in the south of Chile, at Concepción. Which is one of the three big universities here in Chile, together with Católica and Universidad de Chile. That's the only one outside Santiago. So it's actually very nice to be living in the south. And as Tony mentioned, part of the work I'm going to present is in collaboration with the Max Planck Institute for Extraterrestrial Physics. And we started this collaboration this year, which is a partner group. So it's essentially like a mini Max Planck group here down in Concepción, which I really have, a lot of expectations what will come out of this in the future. So I assume you can see my screen. So if you can, Tony, let me know if you can actually see my first slide. Okay, great. Because the other day I started that talk and yeah, I was not showing the presentation. So, okay, good. The talk and the topic that I would like to focus today is essentially very connected to the baryon cycle and the way galaxies evolve. So we know there are these very important elements in the formation and evolution of galaxies. Of course, accretion of fresh gas from the cosmic web is one of them. Then the ability of these galaxies to really eject part of their gas from, very hot to cold gas out of the system. Which is essentially help to prevent future star formation, either by ejecting gas from the disk or stopping the accretion of fresh gas to replenish the fuel you need for star formation. We know that part of that gas is actually recycled and come back to the system, which makes the problem much more complicated. And ultimately, all these different factors playing together determine the way galaxies evolve and the interstellar medium properties of these galaxies across redshift. So in the history of cosmic star formation of the universe, we know there is a time where galaxies were first created, of course, and started to rise as star formation activity, start to form most of stars. They were very efficient in accreting gas, accreting smaller systems, and really increasing the star formation rate. Then there is the time of galaxy assembly, where galaxies created most of the stars we see today in the universe. And then there is a time like today where actually the star formation rate density of the universe decreased by a factor of 30. So what this means is that galaxies tend to live their lives in what we call the main sequence of galaxies, which is essentially, if you look at the plane of the star formation rate versus the stellar mass of galaxies, most of the galaxies live in what we call the main sequence. So that's why these galaxies are usually called either like normal or typical galaxies at a given redshift. But there is also a group of galaxies that fall below the main sequence, that are the passive galaxies or quiescent systems, which is essentially forming less stars for a given stellar mass. And of course, you have the starbursts, the ULIRs, the interacting galaxies, where above the main sequence. And we know this definition of main sequence changed with redshift, in the sense that from this, for instance, from the work by Spiegel, if you look again at the mass star formation rate plot, you see that as the redshift increases, the normalization is higher. So a galaxy with a stellar mass of 10 to the 4 at redshift 0 compared to one at redshift 4, the one at redshift 4 is forming 50 times more stars. And that is considered typical or normal at that given redshift. So the reason why I'm showing all this is because I will be using these terms during the talk, like main sequence, passive galaxies, starburst, etc. So it's important that we all have this information. And of course, because we're going to talk about galaxy evolution, we need to talk about molecular gas, molecular clouds, which is essentially the fuel for star formation. Now, why do these galaxies at high redshift, essentially these normal main sequence galaxies, form more stars? And one of the interesting things about galaxy evolution is that if you look at the molecular gas fraction, which is comparing the molecular gas mass available for star formation relative to the stellar mass, we now know, thanks, for instance, to Herschel, and in a great way, thanks to ALMA, that the evolution of the molecular gas fraction increases in a very strong way with redshift, in the sense that the molecular gas fraction at redshift 2, which is this peak of star formation activity in the universe, is nearly 1 compared to 0.04 in current main sequence galaxies. And you see the same if you go up the main sequence. So galaxies that are above the main sequence also have mass loading factors that are higher. So galaxies are more gas rich. But then if you look at the molecular gas depletion timescale, which is essentially the ratio between the molecular gas and the star formation rate, and if you invert that, is the star formation efficiency, what you find is that there is a weak evolution of the depletion timescale with redshift. And there is, of course, a strong dependence with the main sequence. So galaxies above the main sequence, the starburst galaxies, are more efficient in forming stars. But then if you look back in main sequence galaxies, the reason why they are forming more stars is not because they are more efficient, because remember, this actually dependency is weak. It's because they are more gas rich. So galaxies at redshift 2 are more gas rich. They are probably forming stars that are efficiency comparable to the efficiency we observe in main sequence galaxies today. And that's the reason why we observe this peak. The thing is, galaxies spend most of their lives in this main sequence, which is now shown here as the delta main sequence. So if you go up, you're going to the starburst regime. If you go down, you're moving to the quiescent system regime. And this is a function of mass. So galaxies start to build up their mass, and they kind of oscillate. They go through phases of compaction where they are efficient in accreting gas from the cosmic web or from sisters, satellite systems around them. And then they are very efficient in forming stars. Then they can, by different processes, essentially exhaust the molecular gas available for star formation, and they can go down the main sequence. But then again, they can be, if for instance, the mass of the halo is lower than this threshold by the gas in the halo that's being heated by shocks, you can be again efficient to replenish your reservoir of molecular gas and go up again. But then at some point, this very quenching event happens that will actually move your galaxy from the main sequence to the passive regime. And this is what currently it's a topic of a lot of study and debate, because how is that galaxies actually move from the main sequence to the passive regime is still an open question. I mean, there are many mechanisms that can help, and probably there's not only one that is working, but a combination of them. So I have a list here, but some of them, of course, involve AGN and starburst feedback. For instance, the gas does not cool to really continue forming stars. And here, AGN feedback, gravitational heating, and stellar feedback are important. The gas is just removed from the system. So essentially, you clear out the molecular gas from the central part of the galaxy, for instance, thanks to AGN feedback. Or the cold gas is just rapidly consumed, either by mergers, disk instabilities, or positive AGN feedback. So AGN feedback can actually have a negative effect by removing the gas, or a positive effect by increasing the pressure around the area where the outflow is actually driven, and then enhancing the star formation activity in these areas. So in this talk specifically, I would like to focus on galactic winds, and essentially the fact that these galactic winds can be powered either by starburst or by AGN in the center of these galaxies, and they can have an effect on their ISM properties and ultimately in their evolution. So one very important thing to have in mind when thinking of these galactic winds is that they are multiphase and multiscale. So we know that there are very ultra-fast winds that are launched in the very central engine of these outflows. And then there is ultra-fast accretion disk of highly ionized gas on the very small kiloparsec scales of the central region. And then you have the more kiloparsec or galactic scales winds or outflows that you can detect in different phases, either molecular, ionized, etc., that have been ejecting from the disk at a very, very, very long distances. So studying outflows is essentially very hard. You not only need to look at the different scales, but you also need to look at the different phases. And in particular, in this talk, I would like to focus on three of them: the atomic one, the molecular, and the ionized. So for the atomic, in the studies I'm going to show today, we've been focusing on studying sodium and the C2 fine structure line. For the molecular, it's really the OH molecule and the CO. And for the ionized, the main lines in the optical, H alpha and O3. And why is it important to have a picture of the multiple phases? It's because really, it's really important to understand which one of these phases is dominated, not only the mass of the outflow, but also the energetics. And in that sense, I would really like to say that I'm missing a very important phase here, which is the very hot gas that is really, at this point, impossible to detect in these very high redshift galaxies, but it's also doing a lot of the work. So even if I include the atomic, the molecular, and the ionized, my picture is not complete, okay? So I would like to really look first at emerging luminous infrared galaxies here at redshift 0 or intermediate redshifts. Also, I would like to focus on an example of a quasar at redshift 6, and I would like to finish discussing outflows in typical star-forming galaxies, so main sequence galaxies that are massive, at redshift 2. This is the peak of the cosmic star formation activity, and at redshift 5, when the universe was only 1 billion years old. So let's start with the merging galaxies and the quasar. So the first example I would like to show you is this very beautiful interacting pair of galaxies called IRAS OA572, which has a star formation rate of 70 solar masses per year. It's an interacting galaxy, and it's considered a luminous infrared galaxy because its luminous infrared luminosity is higher than 10 to the 11 solar luminosities. So we observe this galaxy with NOEMA, and what you see here on the upper panel is the CO spectrum. And what we identify is these two wings of essentially high velocity gas that are moving out of the galaxy with a geometry that looks kind of like a bicone shape. So you see here a projected map of the CO gas, but I'm only considering the gas in the red wing, which you see here in red, and in the blue wing, which you see in blue. So essentially, I'm removing the gas that is in the system rotating, and I'm just plotting here the gas that I know it's been ejected from the galaxy with velocities as high as 1,200 kilometers per second, which is very extreme. And I'm surprised about this galaxy is that we also detected this cloud of gas that is moving away from the galaxy at a velocity of about 1,000 kilometers per second. This is what is considered a fossil outflow. So a part of the outflow that is not connected to the main outflow and that is just moving away from the galaxy, and most likely is the result of a previous AGN episode. Because remember that we know that these AGNs are flickering. So the fact that we discovered this kind of high velocity gas, not a cloud, I mean, it's very massive, but that is moving away from the system, that is not connected to the main outflow, really provides evidence for these positive outflow, these fossil outflows, and the fact that AGN are going through different phases of like active and non-active. Then if you look at the comparison of the different phases for the outflow in this particular galaxy, which you see here with the thick gray line, but also for a compilation of other interacting galaxies that you see here in these other gray lines, what you learn is that the outflow mass is dominated by the molecular phase, as we observe in the CO and OH emission. And it's also dominated in the atomic phase, as we can observe in absorption using the sodium doublet. Ionized out, the mass in the ionized is essentially a factor of at least 10 lower than the molecular phase. And then C2, this line that I'm going to discuss in more detail in a few slides, is really like a multiphase tracer. And then if you look at the energetics, so yeah, the mass of the outflow total here is 4 times 10 to the 8 solar masses per year. So it's dominated by the molecular phase. And then if you look at the mass loading rate, which is a term that I've been using in this talk, and it's essentially comparing the mass outflow rate relative to the star formation rate. So it's like these two processes are competing for the molecular gas or the gas itself. So essentially the gas is being removed by the outflow, but it's also being consumed by the star formation process. And then if your mass loading rate is much greater than 1, that's providing evidence that essentially it's the outflow that is depleting the molecular gas more efficiently than star formation. And it's a sign for quenching of the star formation. So in this particular case, you see that the mass outflow rate in the molecular phase is near 10. So it's very high. It just provides evidence how the molecular gas is being quickly removed from the center in a much faster rate than it's being consumed to form stars. And this is not really the case for the atomic and the ionized gas. So these are very extreme examples, of course, because these are merging starburst galaxies, but they already provide evidence that a quenching mechanism that is driven by fast winds that are escaping the galaxy is actually in action in these galaxies. This has been also confirmed by other results looking at the multiphase component of the outflow in other galaxies. This is a compilation by Fruech, which was published last year, and it's essentially a very similar result. If you look here, we have the relative contribution of the mass outflow rate from the molecular in blue, neutral in pink, and the ionized phase in green. And you see that for galaxies like the one I just showed you before, most of the gas in the outflow, the mass outflow rate is really dominated by the molecular phase. So this is a really important phase to study if you want to understand what's the effect of outflows on galaxies. And then more importantly, if you now look at, compare the timescales for depletion by star formation, which you see here on the x-axis, and the depletion time by the outflow on the y-axis. So this triangle here, this corner, is really, is that your outflow dominated. So essentially you are removing the gas faster than consuming the gas by star formation. And it's the opposite, of course, here. Our galaxy, the one that I just showed you before, is shown with a star. And you see that, of course, in these galaxies, the timescales for depletion by star formation and the outflow are comparable. But then you need to understand that not all of the gas that is actually being removed for the galaxy will escape forever. I mean, that will depend on the velocity of the gas that it's being ejected. And if you take that into account, so essentially you compare the velocity of the outflow with the velocity of escape of the system that you can actually model from the kinematics and then to get an idea of how massive the system is, and you correct your depletion time by that factor, you see that in most of the cases, the galaxy will just return to the system and essentially can produce star formation in the future. But for these galaxies that I just showed you, the outflow is so extreme. I mean, the velocities are above 1,000 kilometers per second that you are very efficient in removing the gas from the disk, but also from the gravitational potential of the galaxy itself. So you really, really, really clearing out the gas, and that gas is not coming back on a time scale that will trigger new star formation episodes in the future. So it's really important to have that in mind. Now, that's looking at the CO and what you can learn from direct observations of CO. But there is also the possibility to study molecular outflows in absorption. And for this, the OH molecule has been very useful over the last, I don't know, 10 years. So the idea is simple. Essentially, you have a very bright continuum source, which in this diagram here is a star, but in the case of the galaxy, is essentially a very bright dust continuum source. And you see then in absorption, the molecular gas on one side, and you get this P Cygni profile that you can, it was first identified in interacting galaxies by Herschel. So this is a paper by Eckhart Storm at MPE in 2011, where you see the P Cygni profile and you know that there is molecular gas that it's been ejected from the galaxy in your direction. And this is also has been shown to be a very promising technique to study molecular outflows in high redshift galaxies with ALMA. For instance, in this example published by Justin Spilker for this SMG at redshift 5.3, where you again see the outflow component in OH in absorption. And this is for one object, but there was recently a paper for a whole sample of galaxies at this high redshift. So we look at this with this technique, some galaxies at intermediate and high redshift that I would like to show you now. This is an example of 3 galaxies that are hyperlyrics or lyrics that are very, very bright, for which we really detected the OH emission in absorption with velocities up to 1,000 kilometers per second. So you need to think that this is really molecular gas that is moving this fast from the galaxy and it's being ejected. And in this very interesting case, we observe an inverse P Cygni profile. So really gas that is moving to the central part of the galaxy at a velocity of about 500 kilometers per second, which is something you would expect in these interactive systems. So this is a very nice way to really dissect and understand the molecular gas phases in these galaxies. Now, this is also very important at high redshift because you see here in this galaxy. Tony, yes.
Yeah, I'm just curious, how do you determine the systemic velocity in these systems, and how accurate is that for these?
Yeah, so for these galaxies in particular, we do have many other lines that you can use to fix your systemic velocity, but there are some OH transitions that have some CO lines next to them. So for instance, with one ALMA settings, you can do CO 928 and OH, well, that's OH plus. But essentially, yes, you need a line to set the systemic velocity. And if you don't have one for a particular galaxy, you can find like one setting where you can get one emission line and the OH, so you can compare.
Okay, and so in all of those plots, you put the 0 velocity at
exactly. In all of those plots, the 0 velocity is set by one of the lines. This is, for instance, what happens with quasars. So for quasars at high redshift, what you really want to do is to look at, try to find outflows. I mean, these are quasars. These are very star-forming galaxies at high redshift. And so far, the only very good example we have of an outflow detected on a high redshift quasar is this one I'm showing here from 2012 by Maiolino, which is a galaxy with a very strong outflow. So you can see here in the broad emission and with a mass outflow rate of 1,400. But so at first, I mean, we really thought that then many quasars will come with these outflow measurements, but it's been really hard to detect these broad wings of emission with other lines. So for this particular case, we decided to look at one of these quasars where you don't see the broad emission in the C2 line, but you do have a nice a redshift, as Tony was saying, thanks to the C2 line in the OH. And what we find, I mean, of course, this is the band 7 observations of where we can put when we can observe the OH 119 micron transition. And what we find essentially, it's OH in absorption at a velocity that suggests with a 3 sigma significance, so I'm not claiming anything, this is very tentative, the detection of essentially an outflow on a redshift 6 quasar for which the C2 line is actually not helpful to do this experiment. So this galaxy has no outflow detected in C2, but from the OH, if we can confirm with follow-up observations that we're planning to do in the future, this is really a molecular mass outflow rate of 600 solar masses per year. And now there's been recently the study of really stacking the C2 spectra of many quasars. There is this one example by Bichetti of 48 quasars, and they find that a mass outflow rate of between 100 and 200 solar masses per year. So our result is kind of consistent with what is found for the stacking, but this is again only for one galaxy. So this is very promising, and in the future, we should definitely continue exploring molecular gas outflows at high redshift using DOH in absorption. Now, I would like to move up in redshift. Well, I was at redshift 6, so let's go down to redshift 2 and redshift 5. And why redshift 2? Because we know at redshift 2, we have the peak of the star formation activity in the universe plus the peak of AGN activity. So this is really a crucial time in the universe where on one hand, you have AGN that are driving outflows, and on the other hand, you have to quench the star formation activity so you can start to see this decrease, right, that you see here. So we know from the ionized gas, so the results that I'm going to show here are based on observations of the optical lines in these galaxies, that outflows are ubiquitous in these redshift 2 star-forming galaxies. So if you look at a diagram where essentially this is the main sequence, the black line, above the main sequence, these are starburst galaxies, below, these are passive systems. And then on the x-axis, you have the stellar mass. And the color here indicates what is the fraction of galaxies in this particular part of the plot that are launching or that have outflows in the ionized gas. So if you look for galaxies which has an AGN in the center, there is a very strong correlation with the stellar mass in the sense that galaxies that are more massive tend to essentially host an outflow in their central part. Now, if you look at galaxies that don't show evidence for AGN in the centers, so the winds in this case are driven by star formation activity, we see the opposite trend. So there is no trend with the stellar mass, but as you go up the main sequence, you are more likely to produce its outflows. So this is all based on the ionized gas. So of course the question is, what happens with the molecular phase, which we know is, at least in the local universe, is the dominant phase, right? So if you want to say something about the quenching mechanisms in action in this case, you need the molecular gas. So we focus on one particular massive galaxy, which hosts an AGN at redshift 2.3, and which has an ionized outflow of about 50 solar masses per year. And we look at this galaxy with ALMA, deep integration and high spatial resolution, so really to get kiloparsec scales observations of this galaxy. And of course, we combine that with BLT, AO, Symphony data to look at the ionized gas. So with ALMA, we were able to detect the galaxy, of course, a nice rotating disk. We remove the disk. What we find is that this red wing of high velocity gas that is moving away from the galaxy, and if we project that in the plane, we see that it's going and moving in the north west direction of the galaxy. So just to show that more clear here, we have the rotating molecular gas disk component that I'm showing here in green. And we observe this red wing, which we can attribute to a molecular gas outflow because really there's no HST counterpart on this part of the image that, for instance, can help us identify this emission and associate this emission with another like satellite galaxy, for instance. And it's also moving in the same direction as is the ionized gas outflow. And if you compare, I mean, well, one question, of course, you may have is, I mean, this is really asymmetric. But then if you look at simulations, simulations predict that outflows will be asymmetric. And sometimes you only see one part of the outflow on one part of the disk and not the other, because essentially what you have is like an outflow that is expanding from the very central part of the galaxy, propelled by the AGN, and then the ISM around is very clumpy. So at different times of evolution of the galaxy, you will see this asymmetry in the outflow that is launched. So if you look at the outflow mass, similar to what we observe in the local universe, the outflow mass is dominated by the molecular gas component. Of course, you see here this line here is just show the uncertainties, and it's a lot, and they are significant, essentially because it's really hard to measure molecular gas masses in this outflow, because you need to understand what are the physical conditions of the gas to really convert that emission from CO to a molecular gas mass. But still, I mean, it appears that the outflow mass is really dominated by the molecular component. And then if you look at the mass outflow rate, again, it's dominated by the molecular gas. And for this particular galaxy, the molecular gas depletion timescale, the outflow, it's about half the star formation activity. So really, the molecular gas is being depleted really because it's being ejected from the system rather than by being consumed by the star formation activity. And for this particular galaxy, we know that the velocity that the outflow reach is about 500 kilometers per second. But the escape velocity at the distance we observe the outflow, which is about 10 kiloparsec, is 800 kilometers per second. So most likely this gas is not going to just escape the system, and at some point it will just return and fuel future episodes of star formation. So maybe it's not really the effect of the outflow by removing the gas that is causing the quenching of the star formation activity in this case, but maybe it's just the outflow hitting the gas around and preventing this future reaccretion, or at least delaying the recycling of the gas on timescales longer than 1 gigayear, while it's really suppressing the star formation activity in the future. So we can look at a very simple back of the envelope calculation using models here to understand what will be the fate of this galaxy with an outflow like the one with an outflow like the one I just showed you. So this is, again, the main sequence plane, star formation rate, stellar mass. This is the main sequence, and this is our galaxy, the one that I just showed you. For a galaxy like this, with a halo of the mass of this galaxy, you do expect that the inflow rate to the system is about 240 solar masses per year. Then you can look at the balance term. You can compare the mass inflow rate versus the rate at which the gas is ejected, and the star formation rate, which is consuming the molecular gas. In this case, this factor is about 0.6. So this 256 is what we measure from the ALMA observations that I just showed you. And then this implies that there is a rate of change from the main sequence of about -1 dex per gigayear. So this means that in a gigayear from now, so this is at Redshift 2, then 1 gigayear into the future, we would expect this galaxy to really move about 1 dex below the main sequence and really occupy the passive galaxy regime. So essentially, this is of course very approximated. It's for now a back of the envelope calculation. Please have that in mind, but this could help us to really understand what is the effect of these outflows on the galaxies and the evolution they have on typical galaxies at this redshift. And finally, I will really like to show you these very nice results that I published this year in 2021 of the galaxy when the universe was just 1 billion years old. So this is at redshift 5.5. It's also a main sequence galaxy observed with ALMA. And this is based on a transition which is the C2 158 micron transition, which is becoming super important now with ALMA to really study different properties of galaxies. So briefly, to motivate why is this transition so important to really study high redshift galaxies, I wanted to spend this just 30 seconds on the way the C2 emission is originated. So you start with an OV association that produces FUV photons that will hit the dust. Through the photoelectric effect, you will eject electrons with some kinetic energy that will hit the gas. The gas then will collisionally excite your C+ ions, which then will produce your C2 photons. So the advantage of this line is that it's like a calorimeter, essentially. On one hand, you have the star formation, you have the heating from the star formation activity, and then the gas, at least the neutral cold gas, will cool mainly via the C2 line. So you do expect, if the gas is in thermal balance, this nice correlation between, on one hand, the star formation rate and the C2 emission. So it can help you trace the star formation activity. But because it's the main coolant and it's a multiphase line, it's also very bright and can help you also to study, for instance, outflows in these galaxies. Now, this galaxy can be observed with ALMA at redshift greater than 2. And the plot that I'm showing here is predictions for what happens if you observe with ALMA, full ALMA, 4 hours, from going from Redshift 1 to Redshift 7. And the black line here is a Milky Way type galaxy. So with the C2 luminosity of the Milky Way placed at this redshift. So essentially with 4 hours of full ALMA, you can detect a Milky Way type galaxy up to Redshift 6, which is very, very interesting. The other advantage of the C2 emission is that it's multiphase. It's really been collisionally heated not only by H2 gas, but also atomic hydrogen. So if you look at the radial profile of the surface density of the C2 relative to the CO in H1, well, we know that in H1 it's kind of flat, of course. And the CO is dropping fast from the central part of the galaxy. And C2 is in between. So that means that really we don't have H1 at high redshift. It's just impossible to observe. But C2, it's a good alternative to really try to push to the outer parts of galaxies where the emission is going to be collisionally excited by hydrogen atoms. So outflows in the C2 line have been observed in nearby starbursts with Herschel. This is a paper by Annemieke Jansen, where you see the broad wings here, this high velocity gas. But also now, very recently, have been observed stacking galaxies at Redshift 5. And this is a result by Ginolfi, looking at the Alpine survey, which is a survey of about 80 galaxies observed in C2 at Redshift 5. And again, you see the high velocity wings of this outflow gas. So far, up to this paper by Ginolfi, this has been done using just stacking. So we decided to pick one main sequence massive galaxy at this redshift and go very deep with ALMA. So this has already deep HST observations. And we really try to push the boundaries here and go from like outflows detected in a stacking to outflow detected on a single galaxy. So we observed this galaxy with kiloparsec scale resolution for like 8 hours. We obtained this beautiful spectrum here, beautiful moment zero map, really very high signal to noise detection of the galaxy. And voila, we detected an outflow for the first time on a main sequence galaxy at Redshift 5 in C2 line emission. As you see here, this is the integrated emission in C2. These are different apertures placed in the disk. And then if you look at aperture 1 and 2, you see a component of high velocity gas that is moving away from the disk in the direction of the minor axis, which is kind of what you see in outflows in the nearby universe. Essentially, you move in the direction of the part of the galaxy that offer less resistance. So it's essentially in the direction of the minor axis. And this is now the good thing about the very positive thing about this result is that we are going from detecting outflows at Redshift 5 using the stacking to really detecting outflows for single objects. And if you look at the properties of the outflow, the velocities are comparable to the velocities of star-forming driven outflows at Redshift 2. So velocities between 450 and 600 kilometers per second that are increased with the star formation rate density of the place where the outflow is launched. And then if you look at the mass outflow rate, so essentially comparing if you compare the mass outflow rate to the star formation rate, we find that these galaxies have these mass loading factors between 3 and 6. So really, they are efficient in removing a star-forming gas from the galaxies. Of course, for the C2, the origin of the gas is multiphase. So this is not really molecular gas. I mean, there is a combination of molecular and atomic. So it's kind of harder to make the case for quenching compared to the CO line, which we know is associated to the molecular gas. But still, a mass outflow rate between 3 and 6 is still high and probably has an effect on the star formation activity of these galaxies. And the most interesting thing to me right now, and the essentially focus of the ALMA proposals that I'm writing now, is that C2 is very extended in this galaxy. So for HC4, the galaxy I just showed you, this is showing an integrated map of the dust emission from the dust continuum we detected ALMA. This is the UV rest frame, UV emission from HST. And then you see that C2 is like much more extended than these other two tracers. Could be that because, of course, for instance, for the dust, we are not observing deep enough. I mean, that's one thing we would like to check. But I mean, what we've been discovering is that maybe there is a connection between the outflow that you see in these galaxies is operating on kiloparsec scales and the gas you can detect around. And for going back to the study by Ginolfi, stacking systems at Redshift 5, we see that if you look at the surface brightness profile as a function of radius, galaxies that don't have an outflow essentially have a surface brightness profile that drops at 10 kiloparsec. But then if you look at the galaxies with an outflow, you see this extended component that people have been calling the C2 halo. That's really extending up to a radius of 15 or more kiloparsecs, and then could be connected with the outflow. I mean, how does first you need to find a power source for this gas. I mean, what is heating this gas? It is satellized galaxies that maybe we cannot resolve at this point, or we don't have deep enough observations. Is it really a star formation photons that were created in the disk and that are traveling this far? Is it really mechanical fitting from the outflow that is heating the gas and then it's cooling via C2? I mean, all this is connected, and I think it's super interesting to understand like the galaxy evolution on like the whole picture. And it's really nice that we can see these results with ALMA, and this is definitely, you will hear more from this in the future. So Tony, I think I'm on time, right? It's 45
you
minutes
can
now.
take another 5 or 6 minutes.
Okay, so I can show this slide because this is not outflow related, but I think it's super cool because with the C2, you can also look at the kinematics of these galaxies. Because it's essentially extended, you can really push the kinematics to the outer parts of the disk, which is hard to do with other traces. With JWST, we will now have a look at the optical lines, and maybe we can also do the same experiment from the ionized gas. But at least for the neutral gas, the C2 is really showing a lot of promise. So this is the same galaxy I showed you before, HC4. This is the moment one map or velocity field of this galaxy in the C2. We have detected this beautiful rotation curve at redshift 5.5, which is declining. And then if you model the disk and then look at the contribution from dark matter and baryons, we find that within about 2 times the effective radius of this galaxy is baryon dominated, which is consistent with what has been observed in other high redshift galaxies. And then if you look at the dispersion of the gas in the disk of these galaxies, essentially, so this is sigma naught, so it's the velocity dispersion of the disk. We find that as you go up in redshift, galaxies are more turbulent. I mean, they show higher dispersion, higher gas dispersion values. And in HC4 at redshift 5.5 follow very nice this trend. You can also look at the stability parameter of the disk, so essentially comparing the rotation velocity with the velocity dispersion. And again, HC4 kind of follows the trend and with a value of about 2. So it's really, it's dominated by rotation. But then again, this is a big parenthesis. That's why I put the parenthesis here, just to show you that really C2 can not only contribute to learn about the outflows in these high redshift galaxies, it's also showing like these beautiful results about the kinematics. So
can I ask you a question about that, Klaus?
Yes, of course.
You're got a black X, I guess that indicates the dynamical center of the galaxy.
Yes.
But it seems like it's offset from where the neutral gas is distributed. So do you have a guess as to why that might be?
Yeah, so it's really, it's offset by about 1.5 kiloparsecs. The kinematic center here is coincident with the peak in the gas velocity dispersion, which is a map that I'm not showing. So we are kind of confident that this is really the kinematic center of the galaxy, but we are really looking into why you see the C2 peak of the integrated map kind of displaced from the kinematic center. But yeah, if you have suggestions, Tony, that would be great, because I'm starting to write a letter to report these results. And I mean, because of the dispersion map also, we kind of think that, I mean, we trust that this is really the kinematic center, but you do see that offset. Yes, that's true. So for the conclusions, I would like to just go back to the kind of general picture that I showed you at the beginning. And I mean, we have studied now the outflows from redshift 0 to 2 on like a multiphase scale, which is great. So we have the atomic, the ionized, the molecular components. And what we find is that the mass and the energetic of these outflows are dominated by the molecular phase, which is very important to have in mind, and just shows that in order to really understand how these outflows operates in galaxies, having only the ionized component, for instance, is not enough. I mean, we really need to try to push these studies to the kind of multi-phase level. We have looked at also new tracers of studying outflows at very high redshift, for instance, OH in absorption or C2 line in emission. And what is really interesting here is that we're finding this connection between galaxies that launch an outflow and essentially galaxies that have extended emission around them. So this is going to be very interesting over the next few years to really try to understand how these two are connected. By looking at the velocity of these outflows, we have learned that typically the velocity of these outflows is lower than the escape velocity of the system. So there is an important fraction of this gas that is actually going to be recycled. And the time scale for this gas to fall back to the disk is still being studied by different simulations. And I've been reading different papers that claim that, well, it depends on different properties, but on an order of magnitude, it goes from like 100 megayears to 1 gigayear. And that, of course, is very important to kind of determine what's the fate of the galaxy that you're studying. And finally, in terms of the effect on the galaxy evolution of these outflows, what we find is that these outflows are efficient removing, but remember, not permanently, a cold neutral gas, which essentially helps to delay or suppress star formation activity and can move galaxies from the main sequence to the passive galaxy regime. But still, there are many unknowns. There are many things we need to explore. We need to get more accurate masses. We need to understand better the physics of the gas that is ejected from these systems. We need to understand better the geometry, etc. So there's a lot of caveats here, but I will say the broad picture is this one here. So yeah, that was my talk. Thank you.
Okay, thanks very much, Rodrigo. And we have saved plenty of time for questions. So I guess feel free to unmute yourself or raise your hand. I can call on you, whatever works best for you.
I can see, yes.
Maybe I can start things off perhaps by asking about the connection with quenching that you made earlier in the talk. If the gas is not being ejected at escape velocity, then it would seem that it doesn't really solve the quenching issue. It doesn't really provide an explanation for quenching, or does it? Well, what is your thinking here?
Well, it depends on the time scale this gas will actually return and be recycled to the disk and essentially form new stars, which again, maybe people here know better than me, but from the simulations paper I've been reading, it's kind of an unknown. And essentially, if it is as long as 1 gigayear, probably removing the gas is already efficient enough to quench the star formation activity. But I think maybe the reason why these outflows are so efficient in stopping the star formation activity is because they prevent gas, they heat the gas around the galaxy, and essentially they prevent gas from being accreted to the galaxy, which could be fresh gas, not only recycled gas. So in a way, you starve the galaxy, which was people called quenching by starvation. So essentially, you suppress the inflow of gas to the system, and you just quench the star formation activity because you don't have enough gas to keep forming stars.
And it seems surprising that the most massive galaxies seem to quench more easily, because naively you would think that they have the ability to accrete more material because of their mass. But is your thinking that maybe there's other effects that dominate in terms of the
yeah, they essentially, they also drive more powerful outflows that in a way will affect the physical properties of the gas around, and again can essentially delay this accretion of gas, even though there is gas around to be accreted. It's just harder for this gas to get into the system and start a new episode of star formation.
Okay, any questions from the audience?
So I have a quick question, and you probably explained this early on. So when you were talking about the outflows at high redshift traced in the C2, and Tony was asking about the systemic redshift estimation. And I missed what you said, what reference lines you use as a systemic velocity?
For the one quasar I showed you before, it's the C2 line. So all these quasars have been observed in the C2 line emission, partly because people thought they were going to discover an outflow. So we know well the systemic velocity in these cases, but we didn't see any outflows, except for this case where we have the OH in absorption. But yes, I mean, that's a very important point. To use the OH as an outflow tracer, we do need a good measurement of the systemic velocity of these systems. But that's not hard to do with the C2 line because it's just very bright. So it's really easy to detect these galaxies using the C2 line in emission.
Well, I guess I'm still a little bit confused. So if you're using the C2 line as a systemic velocity, then how do you measure, how do you infer there is an outflow?
Oh, because then you look at the OH line in absorption, and then you see that either like a P-Cygni profile or just in absorption that is displaced from the systemic velocity for velocities that are above 300-400 kilometers per second. So really, it's like offset from the systemic velocity at a velocity you would expect an outflow in these cases. Yeah.
Got it.
So, I mean, when you have very nice data like the one Justin Spilker published, you can even decompose the OH in absorption into like a OH in absorption that corresponds to the system, and then OH that is actually moving out from the galaxy to your line of sight. So it's if the data is good enough, you can even do that, like a multi-component analysis of the OH in absorption.
Mm-hmm. Got it. Thanks.
And you mentioned, Rodrigo, that it took a while to discover more of these quasar-driven outflows. Is it simply that we needed a sensitivity and we just got lucky the first time that the first guy was very bright, but later on we just needed to get the sensitivity to detect these more commonly? Or what do you think?
Yeah, it's still a mystery to me. I mean, there were many ALMA programs that were really very confident of detecting these outflows in the C2 line emission quasars. The OH is different because actually in nearby quasars, if you look at the OH in absorption, it's actually not a good tracer, but because the quasar is at a phase where already clear out all the material around, so it's kind of hard to detect the outflow in absorption. So dusty starbursts or SMGs at high redshift are actually much better. So I mean, the outflow thing is still the fact that you don't detect these wings in outflow still I would say an open question. We know outflow material is out there from stacking, right? I mean, now that we have more than 50 quasars at very high redshift observed with stacking. The problem is that the C2 line only gives you a kind of like lower limit on the atomic gas mass in this outflow. So it's also, from a physical point of view, kind of hard to constrain the different scenarios, because really what you have is a lower limit in the mass of the outflow, not like a measurement. So yeah, I mean, still challenging. And I remember I was part of the ALMA TAC panel last cycle, and there were many proposals that were looking into this, like why are we not seeing outflows in C2 line emission in these quasars? And they were trying to go deeper and with higher spatial resolution to really look at the central part of the galaxy. So I know this is something maybe we will know more in the near future.
Mm-hmm.
Okay. Any other questions? Okay, well, so I guess we'll wrap up on that note. So it sounds like there's a lot more to be done in this field. It's one of these fast developing fields, which I'm sure we will want to hear an update on in a couple of years. So thanks very much, Rodrigo, for joining us today. And we'll be staying tuned to hear more about your results, and good luck with the upcoming proposal deadline.
Yeah, it's coming. Thank you, Tony, and well, thank you everybody for listening
Okay.
to my results. Thank you.
All right. Very, very good. Thanks.